The next type of reaction we're going to talk about is double displacement reactions. This is the switching of the elements between compounds. So if you want to picture this example here that we're looking at, with the A standing for a metal and the C standing for the metal, what they've basically done is they've swapped places with the C and the A. Now, how do we know if this reaction actually occurred? Well, think about all the things we did with single displacement reactions or synthesis or decomposition. We need to see some sort of material evidence present in order to say the reaction occurred. And what we're going to usually see happen is an insoluble material of some sort forms. A gas, a liquid, or a solid, which drives the reaction to completion. In most cases, this is going to come across as a solid, although occasionally we're going to create water as a precipitate. We're going to take a look at an example of a double displacement reaction here. We're going to use potassium chromate and silver nitrate. Potassium chromate is the stuff that's yellow, and in the background to the white, it's a small vial that's white. That's silver nitrate. Now, what's going to happen in this particular case is we've got the potassium and the silver are going to switch spots. So then result, we've got silver, which is a charge of 1 plus, and chromate, which has a charge of 2 negative. When we cross over, we're going to end up with Ag2Cr2O4. Same thing with this potassium and the nitrate. Potassium has a charge of 1, and the nitrate has a charge of NO3, 1 negative. So when that crosses over, we end up with potassium nitrate. Now, what evidence do we have that this reaction occurs? Well, if we watch the video here, we're going to see the silver nitrate is added, and we can start to see this color change. In this particular case, an example of a precipitate forming. That red stuff, you can't see it from here, but it's actually a solid. It would be something you would be able to touch. There's our evidence that this occurred. Now, the last thing we would need to do for this example here is we'd have to balance out our equation. So if we take a look right here, we've got 2 silvers on this side, 2 silvers on that side, 2 potassiums on this side, 1 potassium side on the right. So we need to put a 2 there. And now at this point, this reaction is balanced out. Show another example right here. Skip ahead. Is we've got our 2 bottles. The dark bottle is potassium iodide. The one on the right that's clear is lead nitrate. Now, when we take we add the potassium iodide to the lead nitrate, we're going to see a color change occur. You can see that bright yellow, it looks like paint. Yet again, this is our proof that a reaction occurred. So if we write this out, we would see that our equation would be KNO3 plus Pb. Now, since lead has a charge of 2 and iodine has a charge of 1 negative, when we do the crossover, that becomes PbI2. Now we need to go through and we need to make sure the equation is balanced. We have 2 iodines right here, 2 iodines right here. 2 potassiums right here, 1 potassium on the right side. So we'll have to put a 2 in there like that. Now the question is, one of these is clearly solid. We saw this from the precipitate. Now how do we know if it's the lead iodine or the potassium nitrate? In order to figure that out, we need to know look at the solubility table. And what the solubility table does is basically a cheat sheet to say what becomes solid and what doesn't. Now, you'll always be able to refer to this on a test. And there's one example here, and on the next slide, I have a slightly better example. You'll see these in a handout. But there are 2 things that you can keep in mind. One is that anything that's an alkali, so first column metal, or an ammonium compound, you will always find they perform a soluble compound. So let's use that logic, and let's go back to the first slide. If we're looking at our 2 reactions here, potassium right here, this is an example of an aqueous solution. It's an alkali. So therefore, we know that's AQ. Now, we did see a solid form, didn't we? It was the yellow stuff. So therefore, it can't be the potassium nitrate. It has to be the lead iodide. Yet again, we can take a look. As well, anything that has a nitrate in it, an acetate or a chlorate, these compounds are always soluble. So if we take a look at our slide right here, we can say that this potassium nitrate has to be aqueous. And it has to be aqueous because of A, it's got an alkali metal, and B, because it has a nitrate ion. And that's how we know. This is basically our cheat sheet. Really all you're going to need to know for the first test is this right here. All alkali and ammonium compounds are always soluble. All nitrates, acetates, and chlorates are always soluble. If you see a product, it has to be the other thing. Yet again, I think this is a chart. This is from the old textbook. I think this is a little bit easier to read. But you will have reference to both. You decide which one's easier to read. So how do you know if a reaction is going to take place? The most reactive common materials will always end up in the compounds together. If it's single displacement, if the element is more reactive, it will replace. And we know this from our activity series table. And that is found in your textbook on page 164 for metals, and it is page 168 for nonmetals. For the double displacement, the potential product will always be predicted using the solubility table. Now, if you want to look this information up in your textbook, you will find the one that was on the previous slide was on page 174. So what I'd like you to do at this time, let me just hit next slide. So what I'd like you to do at this time is I would like you to try the 3 equations right here, press pause, and then when you're done, you can check your answers. So in this example right here, what we're going to do is we're taking these metals and they are going to swap spots. So we've got potassium, 1 plus, NO3, 1 minus, cross, and we end up with KNO3. We've also got copper chlorate. So copper, we can tell it's a charge of 2 plus. Carbonate has a charge of 2 negative. When they cross over and we reduce, it becomes CuCO3. Now, which one is the precipitate? Which one is still the aqueous solution? Go back to solubility rule number 1. All alkali metals and all nitrates are always soluble. So if you have one of the two, it's automatically got to be aqueous. If that's aqueous, the copper chlorate, the copper carbonate is what becomes the precipitate. Now let's look at our next example here. We've got ammonium phosphate and lithium chlorate. So yet again, what we're going to do with the alkali metals and the ammonia is they are going to switch spots. So what we end up having is lithium, which is 1 plus, and we've got phosphate, which is 3 negative. When we cross that over, that becomes Li3PO4. Plus, we're going to put ammonium, which is NH4 plus, and we've got chlorate, which is ClO3 1 minus. They cross over, and 1 to 1 is therefore written as NH4ClO3. Next thing we need to do is balance this out. We've got 3 lithiums on the right side, so a 3 has to go right here. But now we've got 3 chlorates. So if you've got 3 chlorates, we have to put a number right here. Now we have written that there's 3 ammoniums, but that's okay because there's 3 ammoniums on this side. This reaction is all balanced. The last thing we need to figure out is which one is our precipitate. Well, if we go back to solubility rule number 1, It says that all alkali metals and ammonium compounds are soluble. In this particular case here, this is an alkali metal, so that's aqueous. And there's an ammonium compound right here. This is also aqueous. Because we have two examples where they're both aqueous solutions, therefore there is no reaction. In order for a reaction to occur, you need to have a precipitate form. Since there are still two aqueous solutions, the reaction did not occur. Our last example here, lithium oxide and calcium nitrate. We're going to take the calcium and the lithium. They're going to swap spots. So we've got lithium, which is 1 plus, and we've got nitrate, which is 1 minus. When they cross over, it's LiNO3 plus. And then we've got calcium, which is 2 plus, and we've got oxygen, which is 2 negative. When they cross over and reduce, we end up with CaO. Next thing we have to do is balance it. We've got 2 lithiums on the left-hand side, therefore we need to put a 2 right here. Make sure lithium's balanced. Nitrate's 2, and that's okay because it's now got a 2 from here. Everything else at this point should be balanced. Now the question is, do we have a precipitate form? Go back to solubility rule number 1. Alkali metals end up forming do not end up forming precipitates. So this is aqueous. And this calcium oxide here, this is a solid. All you're going to need to remember is solubility rule number 1 for the test. But if you want to know the other rationale behind it, you can look ahead to solubility rule number 2. And that says that silver, lead, mercury products are insoluble. All carbonates, phosphates, and oxides are insoluble. So in this particular case here, we've got the oxide down here. And because we've got an oxide, it forms an insoluble compound. Now, how do we know which ways the rules work? If we take a look back at our table here, rule number 1 about solubility is the most important rule. Actually, I'm going to use this diagram here. So anything shown for solubility rule number 1, anything here is very important. For solubility rule number 2, this is always true except when contradicted by rule number 1. Rule number 3 is always followed unless contradicted by rule number 1 or rule number 2, and so on. But yet again, all you're going to really need to know for the test is rule number 1.